Let's do a combustion analysis problem, and we can identify these whenever we see a sample. It could be menthol, it could be just about anything, and we'll get the amount of our original sample. It could give us the molar mass, or maybe not. The molar mass is uh, used for determining the molecular formula. That's the only thing it's used for. Formula. This part right here is used for determining the molecular formula. Then it will tell us, it told us it was burned in oxygen, so hey, that's going to be combustion right there. And it did give us the products and the amounts of our products. We can form an equation of this. In our equation, we'll have menthol plus oxygen yields CO2 plus water. So since we have this equation, it is, and it's not necessary to balance it, but we will know that every combustion analysis problem will have carbon, an unknown X subscript, and an unknown Y subscript for hydrogen, for carbon and hydrogen. It could have an oxygen. So it could have an oxygen. So, and the subscript would be Z there. I'll show you a trick for seeing if it needs oxygen or not, and that'll come up in just a second. It did say that it was 95.6 milligrams for our original sample, 269 milligrams for CO2, and then 110 milligrams for water. So we know that in combustion analysis that we're trying to find the mass of carbon, and since the mass of carbon here is the only place that carbon could have gone to is CO2. It couldn't have gone to water because there's no carbon here, so it only went to CO2. We can manipulate the stoichiometry of this by starting with this molar mass here. So I'm going to circle this. We're going to start here and then start our stoichiometry of 269 milligrams. So that's where this number comes from. Here to here. This is 269 milligrams of CO2. I'm going to convert to milligrams, milligrams of CO2 to grams of CO2. Then I'm going to convert grams of CO2 to moles of CO2, so that I can use the mole ratio of CO2 to the moles of carbon. Then I'm going to find the moles of carbon to the grams of carbon. That's the whole goal, is to find the mass of carbon itself. There's 1,000 milligrams in 1 gram, and there are 44.01 grams in 1 mole. And there is only 1 carbon in CO2, because the subscript of carbon is 1. So it's a 1-to-1 mole ratio. There's 1 mole of carbon to 1 mole of CO2. And then there is 12.01 grams of carbon in 1 mole. I plug it into the calculator and I get a nice little answer of equals 0.0734 grams, or 73.4 milligrams. Very nice. We're not done yet, because we find the milligrams of carbon, because we need to find the percentage of carbon. That's our true goal of the first step. So I need to find the percentage is 73.4 milligrams of carbon to 95.6 milligrams for my total. I got that number, this number, from this number right here. That's the percentage of carbon in my total mass. Multiply it by 100 will give me 76.8% carbon. These are a little different than the answers on the back because we're using different molar mass values here, but they're just a little off, but it won't make a difference in our final calculations. So we got to do the same thing for hydrogen. So I know that there are still 1,000 milligrams in 1 gram, and I know that the molar mass of water is 18.02. That's 18.02 grams per 1 mole. Now, here's a real trick. Before, the mole ratio was 1 to 1. The mole ratio is different for hydrogen. There are 2 hydrogens in water because the subscript is 2. Okay, so there's 2 moles of hydrogen in 1 mole of water. Everybody following my lead there. So, and then the molar mass of hydrogen is 1.01. I plug all of those into the calculator and I find out that the answer is 0.123 grams or 12.3 milligrams of hydrogen. I do the same thing as I did before. Divided by 95.6 milligrams for my total times 100. This number is the same as this number. And it will equal 12.9% hydrogen. Very, very nice. So I have my percent of carbon. I have my percent of hydrogen. So now I'm off to a very good start. Now you may notice 76.8% plus 12.9% does not equal 100%. So that means that whatever is left over, the percent left over, needs to be oxygen. Very nice. So 76.8% plus 12.9% plus some X number of percent needs to equal 100%. This whole thing is 100% of this. So I figure out that since this is percent carbon, this is percent hydrogen, this is my percent oxygen. My percent oxygen is going to be, I need to calculate that. 100 minus 12.9 minus 76.8. My percent oxygen is going to be 10.3. Yeah, 10.3% oxygen. Very, very nice. Very nice. So, usually, if you have 3 different terms, all you need to do is find 2 terms, and then you can just use simple addition and subtraction to find the 3rd term. Now that we've found our percents, we will now have to find the mass. So we found our percents. Then we need to find the mass of each one. That's easy. And then we need to find the moles of each one. You'll see what I mean in a second. Since we found the percents, we're going to assume a 100-gram sample. When we assume a 100-gram sample, it just makes our calculations easy because 76.8% of 100 grams is 76.8 grams of carbon. Very nice. And then we convert grams of carbon to moles of carbon. 12.01. And then we find out that 76.8 divided by 12.01 is going to be 6.39 moles of carbon. Keep doing that. And I get these nice fancy calculations here. Now we need to so now we've found the percents and we found the mass. That was really easy. We just assumed a 100-gram sample and we got this. Then we just converted the mass to moles. Piece of cake. The last step is to divide by the lowest number. So the lowest number is going to be oxygen. So we're going to divide all of them by the lowest number. This is going to be 1. 12.8 divided by 0.644 is going to be about 20. And 6.39 divided by 0.644 is going to be about 10. So I know that C is going to be 10, H is going to be 20, and then oxygen is going to be 1. Piece of cake. That is the whole thing. You're basically just trying to find percents first. Like so. Then just convert the percents to mass. Convert the mass to moles, and then divide by the lowest lowest number, and then round to whole numbers, and that's your empirical formula. This is my empirical formula, but it asks you to also find the molecular formula too. So they could be both the same. Let me check it out. So what you need to do is you need to find the EFW, or the empirical formula weight. That's basically all you need to do is take 10 times the molar mass of carbon plus 20 times the molar mass of hydrogen plus 16. That's 1 times the molar mass of oxygen. And find out that that is 10 times 12.01 plus 20 times 1.01 plus 16. And that equals 156.3 grams per mole. Go back to the original problem. The original problem right here. And see that it told us the molar mass of menthol was 156. Oh, that's very nice. So 156 right here is the same as 156 right here. So that means that the molecular formula must be the same as the empirical formula. This one should be the empirical formula weight, or the EFW that you find, should be a multiple of the molar mass given. So if, for example, if it told you the molar mass was 312, which is twice as much, the molecular formula would be, you would need to multiply all the subscripts by 2 if that makes any sense. So just for this case though, menthol has empirical formula of this and a molecular formula of C10H20O. All right, thanks y'all.